The objective of this lesson is to show you how to use a debugger with C programs. I am taking a look at a file called debugme.c that currently lives in our collection of source code in Linux Remote. If you take a look at this file, you're going to see that there are some interesting things. I declare here a pointer to an integer, a pointer to a character, which could be the very first character in a C string that is null terminated, and then I launch into a main function here that does a few things. One of the few things that this is doing here is absolutely wrong and is going to cause my program to crash. If you don't believe this, we can just get out of Emacs and show you that that is true. So I'm going to invoke gcc debugme.c, dumping the output to a file called debugme. And if I run this, you're going to see that there's a segmentation fault here going on. This message that says core dumped is pretty much ineffectual with your setup on your Linux remote account. There is no crazy file being created with the output of everything that was currently in registers for your microprocessor, but if you tweak with your account setup, after every segmentation fault or catastrophic error such as that, you're going to have all those contents of memory and registers in the microprocessors and the state of the program being dumped to a file, which can get kind of large. But let's not talk about this for now. Let's go back to Emacs to take a look at your program again. It's anybody's guess, if you are not an experienced C programmer, where the crash is being caused. One of the most obvious debugging techniques anybody can use that will work in C and also in any other programming language is to start peppering your code with lines like this one and this one that establish checkpoints for your program's execution. If these strings are dumped out to the terminal, we will know that your program made it that far. Although this tends to work pretty well, in C there are a couple of details that you have to pay attention to. As you can see, I added a third printf statement here at the end of my code, so I now have 3 checkpoints. Got here too, and got here 3. I can exit Emacs and compile my code and run it to see what happens now. When you take a look at the output, you see that I got through to the first checkpoint, and after that there's nothing else that appears. So I am not sure exactly where the crash happened. Going back to take a look at my source code, all that I can figure out from my program's execution is that the crash might have happened between this line here and this line here, which is the last one in my code. Where exactly the segmentation fault was caused, I am not fit to speculate on. Now, if you really think hard and read your source code carefully, you might be able to spot it. And there is no substitution in terms of tools or any other actions to debug your code. There's no substitution for thinking carefully about what is happening in your code. Many programmers debug code in their heads and only appeal to a debugging strategy or tool when that fails. One detail about the use of print statements for the purpose of debugging in C that I need to talk to you about. And that has to do with the fact that printfs use buffered output in Unix. What this means is that when you invoke printf, unless you do something special with the string that's going out to the standard output, that string is first going into a buffer, some temporary location in the program's memory, and at some point it gets flushed and is displayed on the standard output. In a string like this that's not terminated by a new line character, I am not flushing the buffer. So if I go and try to run this, I might not see if this print statement was executed or not. The got here too could have gone into the system's buffer and not have been flushed out to the screen. The obvious way to deal with the uncertainty that is caused by the use of buffered output is to force the buffer to be flushed when we do a print statement. There are two ways to accomplish that. The first one is to insert a new line character at the end of your formatting screen. So that would mean putting \n at the end of this, and any other printf that we use as a checkpoint for our program's execution. When I force the buffer to be flushed right when I want it to be flushed, I can exert more control over my code and then have more predictable results. I can see and learn from this output is that the segmentation fault definitely happened after the got here 2 checkpoint and before the check here 3 checkpoint. Terminating the format string with the \n is not the only way you can flush the buffer. Another alternative, when you can't afford to insert that character, is to follow the printf with the command fflush, passing std out as parameter. What fflush means is file flush, and the name of the file that's being flushed is the argument passed to the function. You can take a look at the man page for fflush to understand it better, and at this point, if I were you, I would interrupt the video, open a terminal, and do exactly that. Take a look at the manual page for the fflush function. In any case, if you exit Emacs right now, compile, and run the code again, you're going to see that fflush produces exactly the same effect as the \n to flush the output buffer. You could at this point, if you are satisfied with the information you gained from putting these checkpoints and printfs throughout your code, and if you already discovered what is the cause of the problem and fixed it, you could just go and zap out each one of these printf checkpoints. And then what you might discover later is that you didn't really fix the bug, and then you have to go and reintroduce the printfs, and that could turn out to be a big pain. What I highly recommend that you do is to use another type of preprocessor directive that causes conditional compilation. That uses the ifdef preprocessor directive, and we're going to wrap all the debug statements with ifdefs like this. You can see here is that I wrapped up each of my printf checkpoints with the ifdef debug and terminated with #endif to close this block here. Now we need to understand what that means. Debug is a literal that might be defined or might be undefined. When it happens to have been defined, by the time that the preprocessor arrives at this statement, it goes and includes this line in the source code. If the literal debug has not been defined, then this doesn't make it into the source code that gets pushed to the compiler. If this is not making sense to you, or if you want to verify that it appears in the output of the preprocessor, you can go back to the first video in this series and take a look at how to intercept the output of the preprocessor. The question that you should be asking yourself at this point is, how do we go and define this crazy literal that we're talking about here, so that when we compile this code, these lines here get actually included into the code that's passed to the compiler? There are two different ways in which you can define a literal. One of them should be familiar to you, even if its usage is a little different from what you've seen before. You could do simply #define debug, and then when you save, exit, and compile the code, just as you had before, gcc -o debug me, your code now will have those checkpoints that we inserted. Nothing actually got better in terms of fixing the bug, but my checkpoints are part of it. And if I go back to my source code, modify it so that I take that define out and compile it again, what I should see is that my checkpoints are gone. I am not exactly crazy about this method of defining literals, however. So we're going to do something else here. Let's go back to take a look at our source code in Emacs. I took away that bound define, and we saw that it's not there anymore. When I compile and run, I don't see my checkpoints being printed out, but I still have my preprocessor code for conditional compilation in there, and I can define the debug literal right here on the command line by doing -D in the name of the flag that I want to define. So -D is equivalent to that pound define for the preprocessor, and here is the name of the literal that will now be defined. When I compile this and execute, I should see that my checkpoints are now back. This is a very nifty way of including source code only on a need-to basis, and you can control it from the command line without having to change your source file at all. I am sure that there was a lot of fun and excitement in peppering your code with printf statements and surrounding them with conditional compilation preprocessor directives so that you could debug your code. But there is a different way and possibly more productive way of doing the same thing by using a debugger. I'm going to show you how to use GDB from inside Emacs. I'm going to open my file, my source code file, as I've always done with Emacs. I am going to divide this screen into two pieces, and in the bottom part now I am going to activate my debugger, GDB. I'm going to do meta x GDB, and the line that contains the invocation comes back like this: run GDB like this, colon, GDB -- annotate equals 3 in the name of my executable debug me. If this name is not present in the line that comes at you, you can just write the name of your executable. And when you're done with that, you press enter. Now you have GDB running at the bottom, and you can type commands such as run in there. You could use a shorthand for run if you don't want to type the 3 characters R, and just press return to see what happens. Your program executes to completion, and completion in this case means crash. So my program ran from its beginning up until it crashed. GDB shows me why it crashed, and it's telling me here something similar to what I see in the command interpreter, that my program had a segmentation fault. If you look up at the portion of the window here, the upper window that has source code, you see a little arrow that is showing me what is the line that caused the seg fault. And if I think about what's written here, I will be able to discover exactly why this caused a crash. But back to that in a second. What I really want to show you right now are a few other commands that you can use in GDB that will help you debug your code. The very first one of them is going to be one that sets breakpoints in your code. So if I can go back to my source code window, I can select any line here in which I want the execution to stop. So I am going to look at the line number at which my cursor is parked right now, and it's line number 11, and I see this right here. So I go back to my GDB window and I type B for breakpoint in that line number 11. When I press return, you're going to see that a little red B appeared in this upper window here. If you are, again, running this on Emacs in one of our Linux lab machines, not directly on the terminal, you're going to see slightly different output. Instead of a B marking that line of code where there's a breakpoint, you're going to see a graphic symbol, possibly a little triangle. Now, when I type run, to execute my program, I'm asked if I want to restart it from the beginning, and I want to say yes to that. My program executes up until here, where the breakpoint was set. And I am now parked at line 11, and I can see what happened with variables in my program that have already been defined and which are currently in scope. So I am running inside the main function. What variables I have that are in scope include int underscore ptr, str underscore ptr, which are uninitialized, I didn't do anything with them, argc, argv, and this integer I. Down here in my GDB window, I can type print, for instance, I, and that will let me see what is the current value of I, and as expected it contains 4. Another way to show the value of a variable is to add the display to it. So I am going to add a display to variable I. That means every time that I execute another line of my code, I am going to be seeing on the GDB window what is the current value of I. For instance, I can, instead of just run my program to completion, which I could do with C for continue, instead of typing the whole thing, you could just press C and then hit return. I will execute my program just to the next line, and I can do this with next. As you can see, the arrow moved down by exactly one line in my C source code. And if I want to repeat that again, I can type next again and go to the next. If instead of spelling next as a complete word with all its 4 characters, I want to just type N, that's fine as well. And I go to the next command. In fact, if I press just return, GDB understands that I am repeating the command which I entered it previously. So by pressing return continuously, I'm always running next. And I ran next a number of times up until I got to this line here, which is line number 27, which apparently could cause me trouble. And if I do next again, I'm just going to type the whole thing to indicate explicitly and clearly to you that I'm about to execute that line, and press return, I can see what happens. Boom, my program just crashed. So now I am absolutely sure that there's something amiss with line 27. There are a couple more points that I want to make before we wrap up this video lesson. The very first one is that there are many debugging techniques out there, and you can try them all. You can find one that's most appealing to you, more comfortable with your learning style or your programming style, but there's one inescapable fact: they all require you to think. And because I'm trying to get you to think, I am going to not give you the answer to what this line does that is making the program crash. I am going to let you open the source code and think for yourself, and possibly try to fix what this program is doing wrong and get it to execute to the end without having a segmentation fault. The second and final parting thought I want to leave you with is that there are many more commands to GDB than meets the eye, and that I want you to go and do exactly what this window is indicating, and use some kind of search engine, most possibly you like Google, to find a reference card for GDB. Choose one of them, whatever it happens to be, go take a look and see what you can learn from it. There are many more options than the ones that we played with, and very likely you would benefit from taking a look at these and finding what else GDB can do for you. I hope you enjoyed this lesson, and I hope you learned a few important things from it.